So we talked about the other day that we talked about the different types of equilibrium constants, and we talked about how to write reactions and identify the K values that go along with it, but now we need to learn how to calculate them. And when we calculate them, there's a few different types of problems that you have to be aware of. So I'm going to go through a couple of them, and then you'll have some homework associated with that tonight. Now, the first one that we're going to do is example number 5 in your notes. It's when we are asked to determine the equilibrium constant when we know all the concentrations of the things that are at equilibrium. So in this case here, we know that we have methanol being made by the reaction of carbon monoxide and hydrogen gas. We are told that the mixture is in a 2-liter vessel, and we are told that we know the number of moles of methanol, we know the number of moles of carbon monoxide, and we know the number of moles of hydrogen. That's all occurring at 500 Kelvin, so we have to just simply calculate Kc. So in order to do that, we want to know our formula, or write our expression. So Kc is, again, products over reactants. So concentration of CH3OH over concentration of CO over concentration of H2, which I'm going to raise to the second power. Now, again, that came from the balanced coefficients in the equation. And because concentration is expressed in molarity, we have to determine the molarity for each of these substances. So for methanol, CH3OH is moles per liter. So I'm going to take the 0.0406 moles over the 2 liters, which is 0.0406 divided by 2, 0.0203 molar. For the carbon monoxide, it's all in the same container. Again, moles per liter. So that's going to be 0.170 moles over 2.00 liters. So 0.17 divided by 2 will give me 0.085 molar. And the hydrogen is moles per liter, which we have 0.302 moles over the 2.00 liters. So 0.302 divided by 2 gives me 0.151 molar. So now I'm going to go and plug those values for the concentrations back into the Kc expression to calculate K. So Kc in this case is going to be my products over my reactants, so the concentration of 0.0203 molar over the concentration of 0.085 molar over the concentration of 0.151 molar squared. So what's going to happen is we're going to take the, so we're going to take the 0.0203 divided by 0.085 times 0.151 squared, and you should get a Kc value here to be somewhere in the ballpark of 10.5. And again, we said that doesn't have units, so we're pretty satisfied with that. The next type of problem that you're going to have to do is you are going to have to, you're given enough information to solve for the equilibrium quantities, but you don't have the quantities themselves at the beginning. So what we're going to do is we are going to go back in time and reuse ice tables, and they're going to basically be the same thing, but I think the easiest way to walk through this is to do another problem. So in this case, we have a closed system, which is important. It means it's sealed. It contains 1 times 10 to the minus third molar hydrogen and 2 times 10 to the minus third molar iodine at 448 degrees Celsius, and it's allowed to equilibrate. Analysis of the equilibrium mixture shows the concentration of the product, HI, is 1.87 times 10 to the minus third molar, and we're asked to determine Kc. So we've been given the reaction, which is balanced as 1, 1, and then 2. So I'm going to set up my ice table. So I'm going to take let's see, H2 and I2 and HI. And in this case, I'm going to now set up ice, which is initial, change, and end concentration. So my initial concentration that I was told for my reactant was 1.00 times 10 to the minus third molar. For my iodine, I'm told it's 2.00 times 10 to the minus third molar. And because we haven't initially made any product, the HI is going to be 0. Now, the change is just like we did when we did stoichiometry, was it's going to be minus the coefficients. So this will be minus x, this will be minus x, and this will be plus 2x. So when I write my expression at the bottom, I'm also told, in order to get there, because I'm trying to figure out these guys here, the concentration of the H2 and the concentration of the I2, I'm also told that the actual concentration of the HI is 1.87 times 10 to the minus third molar. Now, in order for me to figure out what the concentration of H2 is and what the concentration of I2 is, I have to first figure out what X is. And so in this case, I'm going to cheat a little bit, because I could write the expression, which I'm going to have to write at some point. So I'm going to do that over here. So I'm going to say that Kc is equal to the concentration of the products, which is Hi squared, because of the coefficient, over the concentration of the reactants, which is H2 and I2, and those don't get a coefficient. Now, the one thing that I know for certain is the concentration of the HI, which is 1.87 times 10 to the minus third molar, and that's going to be squared. But I know that in this case, X has to be half of what the concentration is. So all I'm going to do is I'm going to cheat a little bit. I'm going to take oops, that's not what I wanted at all. I'm going to take 1.87 times 10 to the minus 3, and I'm going to divide it by 2, and I'm going to get 9.35 times 10 to the minus 4 molar. Now, that's going to be X. So every time that I see an X, I'm going to plug in 9.35 times 10 to the minus 4. So in the case of the HI, 2 times 9.35 times 10 to the minus 4 gives me my concentration that I started with. So well, I'm going to substitute the 9.35 times 10 to the minus 4 in here. And here. And so when I do that, I'm going to get 1.0 times 10 to the minus third minus 9.35 times 10 to the minus 4, and I'm going to get a value for my hydrogen to be 6.6, nope, not 6.6, 6.50 times 10 to the minus 5, and for the iodine, 2 times 10 to the minus third minus 9.35 times 10 to the minus 4 will give me, let's see, nope, I don't want that to be the color because I'm trying to keep them constant, 1.07 times 10 to the minus third. So we have a minus 5. And we have a minus third, and now we can go ahead and plug our values in. So down here, because we're still calculating Kc, 6.50 times 10 to the minus 5 times 1.07 times 10 to the minus 3, okay? And so when I go through and do the math with this, 1.87 second e to the negative 3 squared divided by 6.5 times 10 to the negative 5, further divided by 1.07 times 10 to the negative 3, I get a value for my Kc to be 50.3. Again, no units. Now, moving on to our problem. That next type of problem is we use K to figure out our given quantities. So at equilibrium. So in this case, we're going to use an ice table and sometimes a quadratic equation. We can avoid using the quadratic equation if K is very, very small. If K is really small, initial reactions to concentrations are very, very large, we can avoid using the quadratic equation by neglecting the change in concentrations. If you're neglecting the change in concentrations, the results have to be less than 5%. And if it's not less than 5%, you have to use the quadratic formula. So we're going to walk through two different types of problems, and we'll figure out both of them using the ice table. One will use just an ice table and we'll neglect the concentration change, and one will have to use the quadratic equation. So with number 7, we are told that the equation is sulfur trioxide decomposing into sulfur dioxide and oxygen. We are given a Kc value, and we are given that the concentrations, we have to determine the concentrations of all the species if we start with 10 moles of SO3 in a 20-liter flask. So the first thing that I see that I need to do is I'm going to take molarity is equal to moles per liter. I'm going to take the 10 moles over the 20 liters, and that will give me 0.500 molar. So I'm going to set up my ice table by going okay. So I have initial, change, and end. In this case, I'm going to start with my initial, which is the 0.500 molar. I have zero product at the beginning. As the reaction continues, the change is minus 2x. The change would be plus 2x, and the change would be plus x. Now, when I go through and I bring this down to the bottom, I get 0.500 molar minus 2x, 2x, and x. Now, when I write my equilibrium expression here, I'm going to have Kc is equal to change in products, so that will be concentration of SO2 squared times concentration of O2 divided by concentration of SO3 squared. Okay. Now, in this case, when I go to substitute some things in, I know that I have 1.52 times 10 to the minus 12 will be equal to the concentration of 2x squared times the concentration of x over the concentration of 0.500 molar minus 2x. Now, because when I'm looking at this, I see that I'm going to get a quantity of like 4x cubed on top, I would like to avoid going to 4x cubed, because what will end up happening is I'll get a weird trinomial, and I'll have to figure out a way to solve that. So I'm going to make an assumption, and the assumption is that if the value of x is smaller than, no, not smaller, is incredibly small, words are hard today in terms of spelling, so I'm just going to change my vocabulary to if x is really small, nice job, I can ignore it. I don't know if x is small enough to ignore, but I'm going to go with it in this case. And because I'm going to go with it, I'm going to say that the value, oops, that should be squared, that the value for the concentration of the SO3 is just going to be 0.5 squared. So when I do that, let's see, I'm going to take this and I'm going to page, and when I'm back at my other page, I need to go back and figure out what the value for the concentrations would be. So in the case of SO2, we noticed that we needed a 2x, and for O2 we needed an x, and for SO3 we needed 0.5 minus 2x. Next page here because I need the room, so I'm going to rewrite the expression as 1.52 times 10 to the minus 12 is equal to, let's see, we had 2x squared times x over, which we just said we were negating the 2x, so it's going to be 0.500 squared. Now, when I go to simplify that, I get 1.52 times 10 to the minus 12 equals, on top, I'm going to essentially get 4x squared times x, which will be 4x cubed over 0.5 squared is 0.25. So I'm going to solve for x, and I'm going to take 1.52 times 10 to the negative 12 times 0.25. I'm going to take 1.52 times 10 to the negative 12 times 0.25. Okay, so that will give us, so that will then give us the value of 3.8 times 10 to the minus 13 will equal the 4x cubed. If I divide both sides by 4, I will get 9.50 times 10 to the minus 14, which will equal x cubed. And then I'm going to take the cubed root of that. So when I do that, I will finally get x, and I will take the cubed root of and I get a value for x to be 4.56 times 10 to the minus 5. So I need to go back to, so for SO2, so for what the heck? So for SO2, it's going to be 2x, which will be 2 times 4.56 times 10 to the minus 5, which should give us a value of 9.12 times 10 to the minus 5 molar. For O2, it's just going to be x, so it's going to be 4.56 times 10 to the minus 5. So I don't need to change that, so it'll be 4.56 times 10 to the minus 5 molar. And then for SO3, it was 0.500 minus 2x. Okay, so that's going to be 0.500 minus 2 times 4.56 times 10 to the minus 5, and when I plug that into the calculator, I get like 0.49998 or something like that. So the issue is that it appears that hardly any product was or hardly any reactant was used up. So we have to go back and check to make sure that this satisfies the 5% rule. And the 5% rule says that if X produces product that is less than 5%, then you don't have to use the quadratic equation. So I'm going to take the amount that would be left over, which is 0.499, and divide it by 0.500, which will give me roughly 99.8% is left over, which is good because it's significantly less than 5% that would be used. So this method works. Okay, now when we're going to solve equilibrium problems using an ice table and also using the quadratic equation for this particular one, I'm going to kind of walk through this and show you how this one works. So this is a balanced chemical equation, and I'm going to set up my ice table based on the information above. I have a 1 liter flask with 1 mole of H2 and a 2 moles of I2, and I know that the equilibrium constant, the Kc, is equal to 50.5. So in this case, 1 mole over 1 liter is 1 molar, and 2 moles over 1 liter is 2 molar. So when I go and put these in my ice table, I'm going to have 1.00 molar, I'm going to have 2.00 molar, and I'm going to have 0 for my initial. And because the exponents or the coefficients are 1, it's going to be minus x plus 2x. And so when I write my expression, I have 1.00 minus x, 2.00 minus x, and 2x. So when I go to figure out what I'm left with, I know that my Kc value is going to be equal to the concentration of Hi squared over the concentration of H2 times the concentration of I2. So I'm going to plug in some things that I know. So I'm going to go jump to the other page here. So ice table. When I look at my original concentrations, I have 1 molar for H2 and 2 molar for I is going to be this guy, this set right here. I will post an answer key associated with this, and good luck. So I'm going to take my Kc, and we said that this was concentration of Hi squared over concentration of H2 times concentration of I2. So we were told in the problem that the Kc value was 50.5. We determined that the concentration of Hi2 would be 2x squared, and the concentration of H2 would be 1.00 minus x, and for I2 would be 2.00 minus x, and I think that when we simplify this, we get 50.5 equals 4x squared. Oops. 4x squared over 1.00 minus x times 2.00 minus x. And this time it looks like I'm going to use the quadratic equation. And when I do that, we'll have to come back to this a little bit later, so I'm going to pause this. And so at this point, what's going to happen is we are going to simplify this as much as possible. So I'm going to take the 50.5, which equals the 4x squared on top, and I'm going to FOIL or simplify this business here. And when you do that, you get something like not 2x. 2 minus 3x plus x squared. We're going to pull that out of the denominator, so we're going to have 2 minus 3x plus x squared times 50.5 will equal the 4x squared. I'm going to distribute that, and when I distribute that, I get 101 minus 151.5x plus 50.5x squared equals 4x squared. I'm going to set that equal to 0 because we're going to use the quadratic equation by subtracting both sides from 4x squared. And when I do that, I get 101 minus 151.5x plus 46.5x squared equals 0. Now, I'm going to take this expression and I'm going to put it into the quadratic equation, which I am very aware that you know how to use, and some of you probably have programmed something into your calculator to make that work, but in the event that you sort of forgot, this is your quadratic equation. In this case, I'm going to take x is equal to negative 151.5. 51.5 plus or minus the square root of negative 151.5 squared minus 4 times 46.5 times 101. All of that business is over 2 times 46.5. And when you go through all of the math, you get x is either 2.32 or x is either 0.935. Now, this is the important part of this. You're probably wondering what to do with both of those values because really only one can work. And the answer to that question is when you go back to the original, and since this one right here is bigger than both of them, we can't use that one. So that tells me, and that's the way that you go about deciding which x value to use, that this is going to be the true value of x. So now I'm going to go back and I'm going to figure out what the concentration of H2 and I2 and HI is. So we said that H2, the concentration for H2 was equal to 1.00 minus x, which now this time we're going to say is 0.935. So the final concentration at equilibrium is 0.065 molar. For I2, it was 2.00 minus x, and so now we're going to take the 0.935, and when you subtract that, you get a value of 1.065 molar. And then lastly, concentration of HI at equilibrium is equal to 2 times x, which in this case is going to be the 0.935, and when you multiply that out, you get a value of 1.87 molar. So, in a way to make sure that you've done this right would be to go back and check. And if you plug all of these concentrations into your Kc expression above, you should get the value that you were told Kc was, which was 50.5. And so if we wanted to check that, Kc would be equal to concentration of 1.87 squared over the concentration of 0.065 and the concentration of 1.065. And so if I take 1.87 squared divided by 0.065 divided by 1.065, I get a C value of 50.5. Congratulations, you've done this. Your homework